So it's great to be here. It's obviously a privilege to be standing here giving this talk. It's a privilege and an honor to be getting the Dal Nygaard Prize. I always kind of said to myself, that's really the only prize in computer science that I really ever wanted to win. And so I feel lucky and privileged to be here giving this talk today. The talk's called Half a Life in Software because, well, even if it's the senior prize, I hope I'm not quite done yet. And that, I hope there will be more stuff that I get to do in what I hope will be the other half of my life. Yeah. As most of you know, I'm James Noble from Wellington in New Zealand, and I always get asked what the Maori words for my university means. Te whare wānanga o te opoko o te ika Maori, which means te whare, the house, wānanga of learning, so the house of learning, the university. O te opoko, of the head, o te ika, of the fish, of Maui. So the university of the head of the fish of Maui, because the head of the fish of Maui is Wellington in the Maori understanding of the world. Nosti Seitun. Kirsten Nygaard. I'm going to start by talking about Kirsten because of Johan and Kirsten. Kirsten was the one that I knew. We had the advantage, I guess, or the disadvantage, towards effectively the end of his life, that both of us would go to Uppsala from basically the same distance on the other side of the world, one from Norway, one from New Zealand. And so we would arrive at the Uppsala Conference Hotel at 10 o'clock at night, and then he'd say, go to dinner. I'm not sure he knew my name. He always called me Kiwi. And we'd go off and have dinner with Kirsten, and there's another picture here which in some ways reminds me more because it looks like he's in a bar. And the thing I remember about the dinners with Kirsten, which is why I can't remember any of the content, is he would always insist on ordering a good bottle of wine, at least one good bottle of wine. And then after that, at the end of dinner, it would be, Kiwi, we must have grappa, we must have grappa. So we'd have a glass of grappa. And then when we'd finished that, another glass of grappa, at which point I can barely walk, and I'm completely jet-lagged, and I thought it was terribly unfair that Kirsten would be able to get up, walk off to his room, and then get up in time for the keynote in the morning, where I would sort of be rolling around. If I made it at all, I'd be shambling in late. Another interesting thing about this is this website this picture comes from is from klassekampen.no, and as far as I can understand, Klassekamp basically means class struggle. So in fact, not just as well, but as part of Kirsten's contribution to computer science, he was very interested. He was a member of the Vestra, the Left Party, the Liberal Party. He worked with trade unions. So a contribution of Kirsten's I'm not going to talk anything more about today is his involvement in setting up the Scandinavian School of Participatory Design in information systems and through to computer science. Designing computer systems, co-designing computer systems with the people who would actually use them, with the people who were supposed to benefit from them. And I fear I have to mention the other thing, of course, Kirsten Nygaard did was keep Norway out of the EU. Nostai Seitun. Or since we're in Rome, teme nosce, know thyself. In this talk, I guess, because I get to do it, I'm going to be talking a bit about myself. I want to talk about some of the work that Kirsten Nygaard did, which I think shaped the work that I did, some of the other important influences on the research and the contributions that I've made, and also, I hope, talk a little bit about some of the things that I'm still trying to do in my research and in my work. So although I was born in the same year that Simula 67 started, my first computer was in 1981. This is the ZX81, Clive Sinclair. It had precisely 1K of RAM. And the interesting thing about it, if you can see this keyboard here, there's all sorts of funny characters on the keys. That's because of two things. It had a structure editor, so it was impossible to make a syntax error using one of these computers. Another nice thing the manual said actually is you can never damage this computer with the software that you write. If it all gets hosed, you pull the plug out of the back, you plug it back in again, and you're right back to the beginning. And the other thing, you could write more or less about a page and a half of BASIC on the ZX81, and the reason why, and the Spectrum, which was a successor computer, the reason was, again, it's got all these symbols on the keys. The reason is because in conjunction with the structure editor, the way these things worked is you actually typed basic bytecode directly into the memory of the computer. If you're sitting in a situation where the thing wants an opcode, then hitting the L key inserts the let bytecode, and then it wants a variable, and the key will let you type a variable, and then it wants an expression, and then the key will presumably have got to type equals. It won't let you type anything else. And so because you're directly typing in the bytecode, this was the way you could manage to get a page and a half of code and whatever else was necessary to run the computer, in the case of the ZX81, in only 1K of RAM. But eventually, being from New Zealand, still looking to England, all these computers, and it moved on to the BBC Micro, which, as you can see, doesn't have a chiclet keyboard. It's got a proper keyboard, and of course that meant I had syntax errors. So these were basically the computers I had at home. We had BBCs at school, and then eventually I got to university, and that meant I switched from one of these things to one of these things. This is actually a digital VT52, and we didn't have the real ones made in America by Digital Equipment Corporation. We had ones that seemed to be ASCII terminals that seemed to be built out of raw steel somewhere in Eastern Europe. They spoke ASCII, I'm sure they weren't. And the experience was a little bit different, going from these microcomputers that were at least responsive to sharing a VAX 11780 with 150 other people, talking to it over a 1200 baud serial connection, if you were lucky. If you were unlucky, you had to go into the overflow terminal room, where they multiplexed 5 or 6 terminals across exactly the same capacity line. And the thing at the other end of the wires, as I said, a VAX 780, that's got a compute power. Well, it depends how you measure it, but not that much different from the BBC Micro, except the VAX was 32-bit and the Micro was 8-bit. But around the same time as I was starting in this, even in New Zealand, in the shops, these things were appearing in a Mac. Okay? And it seemed pretty obvious to me then that, this was, if you like, the way of the future. The VT52 was the past. This was the way in which people were going to be interacting with computers. So, we're all familiar with this. It hasn't really changed that much, except I guess the screen resolution's got a bit better. Look, the Apple symbol, these menus are still the same. Still bitmap graphics, still interacting mostly with a mouse or I guess a trackpad. And the display here has, well, what does it have? It has these things you manipulate, these objects. And what we have here is a model of the world. Well, in fact, if I actually said to somebody, it's on my desktop, these days, of course, we probably mean it's on the virtual representation of the desktop rather than actually on the physical desk. So it seems that was the way that was going. But and in a graphics course, I think I did get an opportunity to program the Mac, and it was really quite disappointing, because at the time the Mac programmer's workbench, basically you loaded up this thing and it turned the Mac back into a VT52. You got a command line and you compiled C code, or if you were really lucky, Object Pascal, and it crashed, and then you went round the loop and round the loop. But again, at around the same time, being a somewhat sad young man who frequented the computer science shelves which were in the basement of the library, I came across this book. And This is obviously the Smalltalk book. Hopefully everybody in this room, considering that it's ECOOP, has actually read the book or knows about it. For those of you significantly younger than me, a book is paper that... Actually, I lied. Due, I think, to Stefan Ducasse and the Faro guys, this book is available as a book, as you will understand, as a downloadable PDF file. So you've all really got no excuse if you haven't looked at the Smalltalk books to go and look at it. And this seemed like the future. And in fact, this is nominally 1980, and I figure for the best part of 20 years, the Smalltalk programming environment was the future. And there was very little, certainly very little people were actually using to build programs with a programming environment that was actually as good as Smalltalk. And perhaps this isn't quite the Mac because it's all being done with text, but we've got reasonably nicely rendered proportional fonts, and clearly the way you interact with this is by selecting things from the menus and typing stuff in. And you can still get syntax errors, but due to the design of Smalltalk, you only ever edit one method at a time. So the syntax errors tend to be relatively easy to hunt down. So there was this stuff that I was reading about, and I also staggered across this, which, sorry for the low resolution scan, the only one I could find. This is an ACM distinguished dissertation from, that says, I think 1987, Algorithm Animation by Mark Brown. And this again described a program that ran on the Mac called Balsa. And what that program did was you were able to run, well, primarily sorting algorithms, and the program would show these things operating. And so if you have looked at these enough or know how to read them, this one, for example, is quicksort, heap sort. The quicksort one, I think, is the most characteristic because you can see here x equals y, this part of the array or whatever is sorted, and there's obviously been a partition here, and then there's one of the partitions, and we're currently partitioning here, and we're sort of recursing down there. Okay? And I think I remember talking about it in the doctoral symposium, and one of the students said, "Oh, you mean like the displays that are on the Wikipedia page?" So it's quite interesting that this stuff has now more or less got into the way that we teach programming. It's on the Wikipedia page, and were I to teach a first-year algorithms course, I've only ever done it for 10 for various reasons, I might use something like this. I wouldn't use this, but I'd use something like this. And so, again, here's a different view. You can see quicksort running, and then this view here shows the recursive partitioning that the sort is doing. So that's all right. The catch is that in order for this to work, you have to annotate the algorithm. So here is some of the code that's inside the stuff that's running on Balsa, and what's happened is there's the code that actually does the swap, and then we put in these event procedure calls to say, okay, I've done a swap, this thing is now in place, I've accessed this here, I've accessed that there. So yes. As a dog returns to his vomit, so a professor returns to his thesis. This is actually the system I built. Doesn't run anymore. In Self, actually, for my PhDs, used to do something similar. So this is actually event trace that my system would produce out of quicksort. And you can see there's recursive calls to quicksort, accesses to the array, calls to swap. The difference between Balsa is that I could do this. You had to write quicksort a little bit carefully, but you didn't have to put in all these event annotations to tell the visualization system what was going on. Why? Well, the reason why is because it's object-oriented. So you might, for example, have a vector down here that is the thing you're actually sorting, and our system put what I called an encapsulator, and now you might call it a transparent proxy or an intercessor or a chaperone around that object, and that was then connected up through to the view. And this meant that whatever operations the array undergoes when it's sorting, they can be displayed. So, we can produce pictures like this. There is the classic views of the array, traces the operations. We've got information about the recursive calls coming out to the methods on the object and the methods sent to the object itself. So we can display these sort of quicksort partition views, etc., etc., etc. And again, the reason we can do this is because each object is representing an abstraction, is modeling something in and of itself, and so we can use that information to produce all the information we need for the views. As is traditional, the high point, if that's the right word, of my thesis was a visualization of a compiler. Again, this was another system that had been the illustrated compiler that had been done a while before I did this. But again, that was done with a lot of annotations being put into Lisp code. And here, everything is reified. There's a parse tree, a parse stack, a buffer of tokens being built up. And I think you can actually see the input cursor. It's just sitting there. It's just read the token total. And all of this without annotating the compiler, all of this simply by monitoring what the program does. There is an FSM here which is doing the parser. Obviously it's parsing that identifier total. All of this without annotating the program. Why? Because the structure of the program encodes the abstractions that we want in our model. The first half, and the other half is even in self, because the idea that these abstractions are encapsulated, they are protected. An object is responsible for its own state and its own behavior. If you look at an object, if you can see an object's interface, you should be aware of all the behavior that that object will undergo. So, to quote William Cook in his great paper on understanding data abstraction from Oxford 2009, says, an object can only access other objects through their public interface. And then he goes on to define the term autognosis, which means self-knowledge. An autognostic object can only have detailed knowledge of itself. And he goes on to say, any programming model that allows inspection of the representation of more than one object, more than one abstraction at a time, is not object-oriented. Okay? It's a strong claim. We're going to talk about that a bit more. An object can only know itself. What's the problem with that? Okay, this goes out to Tobias if he's in the room. The problem is that aliasing is endemic in object-oriented programming. This is a quote from a paper we worked on with John Potter and Jan Vitek, and it was in fact the first ECOOP paper that I ever had. The problem is, and as Vieth put it, pointers are the go-tos of data structures. There's this great table which I found very hard to actually track down. I think I scanned this out of an Oberon version of the book Algorithms and Data Structures. And what he's saying is, look, atomic elements, assignments are scalar types, repetition and for statements go with arrays. If it's definite and if it's indefinite, well, there's sequences, and down the bottom, recursion, procedure statement, or recursive data types, and then down the bottom, the general graph, the go-to statement, the structured link by pointers. Okay, and we know that go-tos are considered harmful, so I guess pointers are considered harmful as well. Here's another slide from that, or an image from that paper. And so here is our stack that we're trying to visualize, say. And there it is, the object representing the stack and some of the stack contents. And here's the array holding the contents. And the catch is this little object D over here has got access to this contents object. And what this means is that the interface of this object A here is no longer the interface of the whole abstraction, because the whole abstraction isn't encapsulated. Because you can get at this contents array, you can add things and you can remove things without going through the nominal interface of that abstraction. And that way, for example, in my system, you are going to defeat the visualization that I'm going to do. And of course, this is, in many senses, a wider problem. If you're trying to put concurrency control around an object, if you can just put concurrency around an abstraction, if you can put it around one object that implements an abstraction, that's relatively easy. Once you've got all these incoming pointers, these aliases, it gets a lot more tricky. If you want to protect an object's invariant, so an object can always know that its internal state is consistent. Once again, if it always knows it's being accessed through the object that represents that abstraction, that's easy. But if it has to take into account pointers coming in from anywhere else, these go-to statements in the heap, it's a lot more difficult. So the idea in flexible alias protection was to say, okay, let's try and lift these objects to abstractions. Let's put a boundary around what in the paper we called alias protected containers. The word ownership didn't come until later on. So we'll say the hash table owns its two arrays. And these things can have references out to other objects. So this structure is not an entire tree because these students, say, might, for example, be enrolled in more than one course. But what we aren't allowed to do is have these incoming references into the implementation of this array. So in my case, if you just monitor the execution of the hash table object, you'll still get all the information you need about the important stuff to do with the array. And the nice thing about this approach, again from flexible alias protection, was the idea if you set this up carefully, these kind of things could nest. So, for example, the hash table could actually belong to a course object. Perhaps the marks that are stored in the hash table could also belong to the course. But that still doesn't mean that the course via the hash table can't refer to these students' objects that are outside and can be shared, can be enrolled in a number of courses. But the key advantage of this is both the hash table and then the wider course abstraction of which they are a part, again, have control over what they represent, control over their invariance, control over their state and behavior. In other words, that they can know themselves. Where did this carry on? Well, hopefully most of you will probably know the story, but the other contribution in the paper, it said, look, we think you can do this with some kind of syntactic control. We called these things alias modes. And so in the declaration of the hash table, we said, well, the hashable, the keys and the arguments here are going to be outside this container. They're the arguments you might put into the container. And the actual two arrays here are part of the representation. Methods would be annotated to say, okay, what's going on here? It's not returning anything. You've got to have something that's a K. You've got to have an argument here that's an I object. And when you call get, what you're going to get back is an object that belongs to this set I here. And of course, in order to protect the representation, you weren't allowed to return anything that was rep. So in the flexible alias protection paper, this was all essentially speculative. Various people have said, there was no implementation, there was no type system. How on earth did you ever manage to get it in? Well, as I said, I feel privileged to be here and very lucky. But in some ways it was a bit prescient because around the time this paper was written, a very talented student of mine, David Clark, came back from Tasmania to Sydney, where I was actually working at a Microsoft-funded research institute at the time, and basically said, I've given up writing my novel, I'd like to write a PhD. And I gave him this paper and said, well, he understood mathematics. If you can manage to formalize this, there's a PhD in it. And it turns out there was, and by UPSLA the same year, Dave had invented these things called ownership types. And so here again, we can see a class declaration. In this case, if it's a link in a list, and the type of the data is X, but the owner of the data here is N, and you can see this is kind of threaded through the link. So it's parameterized. Owner here means that this next link will be owned by the same person who owns this link. And that information is threaded through, so we can see a stack which is using the link. Once again here, we say this link is owned by the representation of, it's part of the representation of the stack. All the links are going to be part of the representation of the stack, and then the data is threaded through. Catch with this approach is, well, you've got these parameters, but you can see here the data types are fixed, and this was 98. And for those of you who were around in the early noughties at UPSLA, the big thing, of course, was generics. There seemed to be entire years of the conference devoted to designing generics in Java. So, of course, we had to join the party. And again, another student of mine, Alex Pachanan, also working with Dave Clark, designed this form of generic ownership. And the interesting thing about this is in this map, we only have one parameter here for the key. And that parameter carries both the alias information, in fact, it's kind of embedded in the type here, and, key extends comparable. That is the basic standard constrained generics that you would have in Java. So these type parameters are able to carry both ownership information and the type information, a polymorphic type information that we're so familiar with. Instead of saying rep, we said this because, well, the object belongs to this object. So again, I think this is a map, not an array. So there's a single vector here which says, okay, it belongs to this. And this vector, again, is parameterized with nodes, and the nodes belong to this. And the nodes map key contains keys and values, and those keys and values, again, come from the parameters here, both the ownership and the types. Where did this all end up? Well, in some sense, it ends up here. I don't really speak very much Rust, but I did manage to get to GitHub and take out what Rust actually has for its hash maps. And this is a declaration, and as you can see, here are some type parameters, and they're sort of, in this case, they're wired up into an inner resized table, and you can see the ownership types parameters there, right? Okay, actually you can't see the ownership type parameters there in this example, because what Rust has done is the kind of thing that Alex and Dave did in generic ownership. These parameters also, as well as carrying the type, carry the ownership. Rust has a slightly different syntax based on ML's type parameterization, which lets you break out the ownership types. So, for example, for an iterator, there's this extra parameter here, apostrophe A, which represents some ownership context. And then here we've said, look, at this point, the key and the value slots, they are both going to be owned with the same owner A. You can put those kind of things on struct declarations. You can put those kind of things on methods. So here's a fairly complicated method that I'm not going to explain because even I don't understand it. But we can see here an ownership parameter is coming in here. It's used to mark the ownership of this first parameter called self, and connecting through to the internal table entries which are related to this thing. Okay. The other thing I want to point out about Rust, yes, they've used the keyword struct there, and there's this debate, should I be talking about Rust at ECOOP? Is Rust really an object-oriented language? It doesn't support proper inheritance. Well, maybe it doesn't. But on the other hand, when you start writing code with all these methods which have self as a first parameter, and you're making calls like this, self.makeHash, self.table, well, I think if you're using self like that, the language is considered as object-oriented. Know thyself. The other thing I did in my PhD was in self. Did I mention that? And famously, self was prototype-based. This is the self user interface running on a Mac. You can go and download this software originally by Dave Ungar and a bunch of clever people who went and founded Google or helped Google and all became multi-millionaires. No? You didn't, but the rest of them did. Urs Herzley won the most. Dave didn't, and he was bitter about that for a very long time. If you get him on a good day, he probably still is. So here we find these things represented with objects, and these objects are prototype-based. So the theory goes in self there aren't any classes. Instead, we just have objects, and these objects can have these delegation links, parent links, that kind of work like inheritance. So, this is some kind of graphic, and there's the way self-organized, you say, okay, there's these traits object that hold the methods, there's this object here that actually holds the field, and if you send a message in here, I don't know, maybe print string or register, say, if it's not found in this object, we go up the delegation link, we go across the delegation link, we find it there. And this clearly is a simplification of, well, certainly similar, definitely Smalltalk, where classes were baked in at the conceptual level of the language really hard. Okay? What's the catch though with this? And this is actually a bit of a talk that I find quite difficult because I did work in self and I have great admiration for Dave and Randy and the conceptual cleanliness of their design. But let's just think about this. Let's say we have a print string method here, say, and let's say we add in an extra slot here. Okay, so we'll use the self UI, and we'll add an extra slot into here, and we'll modify the print string method so it's going to rely on the extra slot. What will happen if I then try and print this object? well, presumably it might delegate up to that print string, that might well resend here. This thing is going to call the extra field, and then it's going to crash, because the extra field isn't in this prototype. So it turns out in self, what you actually need to do to set up inheritance is, if you want to put a field into what you could think of as a superclass, or a super prototype or a higher trait or something, you also have to make sure that that field is added in to all the prototypes of every trait that is going to inherit from it. I'm not sure if the projector probably isn't quite good enough to show this, but you can actually see perhaps that this slot, the extra slot, and the X and Y slots in this prototype here are actually a slightly different color to the rest of the things. And this is because in the later version of self, the later version of the self user interface actually had support for maintaining this. So there was a button you can press and it says copy down parent. In this case, this object over here, graphic. And what that means, and slots to admit parent, what that means is whenever you add an extra slot here or delete it, the self-user interface is going to hunt down every object that has this copy down parent relationship to this one and add the extra slots in. Okay? And in fact, it actually goes one step further than that. In later versions of the interface, the menu got a subclass me button. And if you point the subclass me button at one of these objects and press it, it goes off and builds this structure for you, where the slots will be copied down and all these things are set. It builds a new trait object, builds a new prototype, and then winds up the copy down. So here, in this object, all of these slots are being copied down from here, and some of them being copied down from there. So I spent a lot of time working with prototypes and prototype-based languages with a lot of clever people. But this is a problem with the self model of prototypes, I think. I'll talk a little bit later about the language I'm designing, Grace, with a bunch of people, Andrew and Kim, who are in this room, and Tim and various people who aren't. I always thought if I was going to design a language, it would be based on prototypes. But because of situations like this, it seemed that doing it this way wasn't necessarily the best idea. Okay, perhaps there is an objection. This is the self way of doing prototypes. This is prototypes really, really 1990s. Now, prototypes have been improved by JavaScript. Instead of having these things, I mean, this is really classy. You could basically look at this and say, come on, James, that is the memory layout of Smalltalk objects and Smalltalk classes. Who are you kidding? The right way to do it is like this, where here is an object that's got both the methods and the slots for the graphic, and here's the one that makes it a rectangle adding in the height and width, and here's the one that I'm building, and each delegates to each, and it's all fine. Why didn't we do it that way? Why didn't we do it that way? Well, this way also has several problems. Notably, that if I go into this object here and ask it to clone itself, do it in the self-user interface, what I get is this. Okay, I've cloned this object, and I get an object here, but it's sharing the rest of the structure. Okay, if you think about what makes up an object, these things, in a sense, make up the wider sense of the object. Self would say parents are shared parts of objects, of the abstraction represented here, but it's pretty certain I didn't want this new object to be sharing the height and width and x and y value of that. How can I do to get around it? Well, once again, this is self, so I can just stick a new method into this object, and there's this wonderful self code here, obviously very straightforward, parent.clone, parent::parent clone. And what this actually means is I'm defining a method called clone, so this is pretty much a supersend up to here and saying run this thing's clone method, and then when you get it back, assign the parent field of the object, because once we've done a clone, the parent field will still point up to here. We'll assign the parent field of the object to the new object that we've created. Okay? So far, so good? Oops. We're only halfway there. Okay? So you can basically do the same kind of thing, put parent.clone in here, and eventually get to a structure that when you clone will reproduce the wider structure of the object, the wider self. So these kind of problems, the split object problem, also called object schizophrenia, where if an object is made up of all these various parts, you can get references into the middle of them, even if in some sense you're not supposed to. Having to write this kind of stuff every time you want to clone an object. And related to that, because here I'm assigning to the parent of the new clone, that means that the parent slot, the slot that I'm inheriting from, has to be mutable. And back in the days of self, and still now in JavaScript, if you start inheriting through mutable slots, your performance just goes down the tubes. And it's related to another problem, that constant definitions in the object. In self, points are supposed to be immutable objects. You do something with a point, you always get a new point instance, maybe with different values. You could, in theory, share point instances that all have the same coordinates. But when you build things in self, they have to have, though the fields holding all those things have to be variable, because when you do a clone, you have to be able to assign to them. And in self, once you've done that, those fields have to be variable, have to be assignable. So when we came to designing the language we're working on called Grace, I'd always thought if I was doing this, it would be prototype based, or at the very least, I might have some sort of syntax which gave me classes, but in fact, I would implement that by compiling down to prototypes. But in fact, what we ended up doing was going back to Cresta-Nygaard and going back to similar. So inheritance and similar isn't called inheritance, it's called prefixing. And the way you do it is you actually stick the name of the superclass prefixed onto the class declaration that you're working with. And if you're mad enough to go and read the Simula 67 common base specification, they have diagrams like this, where here's what we now think of today as an inheritance hierarchy, and they explicitly say the way to think about that is, this class C here is building objects where there's some A stuff prefixed onto some B stuff, and that's prefixed onto C stuff, and where these things are all a single object with a single self, and so that when they compute, they always know what they're doing. In Grace, we tried to carry that on, and I don't think we've got there, and the design of Grace is only up to version 7.7, sorry, so I still have hope. But the idea was, say you write some Grace class definitions like this, under certain circumstances, and I have to stress under certain circumstances, or Michael Homer will curse my soul forever. The classes are in the same lexical scope, the classes don't have parameters in particular, and these expressions here are very simple. In theory, you can take all this code, say delete most of the class declarations, and say that's equivalent to a declaration of a class like this, where bottom just has all the methods and all the features that have been inherited. This, again, isn't a particularly new idea. Some trait systems do this, and particular Eiffel, again, way back in the mid-80s, had the idea of a flattened form. What's interesting is even in Eiffel, this wouldn't really work. And the reason it wouldn't really work is because in Eiffel, these class declarations also created types. So if you do this kind of flattening, these types either aren't in the program, or if you flattened each one individually, the types are still there. But this object here won't have those types because they're not explicitly declared. One of the interesting things about Grace is it's a structurally typed language, so any object, any class that declares methods and that conforms to a particular interface will have that type. So you could actually do this in certain circumstances in self, and your code will actually continue to work. If you want to know more about this, Tim Jones, my talented PhD student, soon to be finished. Am I allowed to say you're looking for a job? Well, a bit late. You're looking for a job. We'll be talking right here at 3:30, going into this with a model he's built of this in mathematics and Redx in more detail. Okay. So here's another interesting thing. We have William Cook's rule that an object can only access other objects through their public interface. Okay? Let's say we I don't know, we want to check, for example, that the bank that I'm depositing money into is the bank that you think you're getting. In a language like Java, in most object-oriented languages, not all, but most of them, you can do that by writing a sort of language-level third-party comparison, where the object with this method is sitting outside of the two objects it's comparing, and it can say, are these two objects equal? And that means something at a very low system level. You know, are their objects' identities equal? Now, the nice thing about that, of course, is it's 100% trustworthy because the system has to provide this behavior. The not so nice thing about that, especially once you start thinking about a concurrent system or a distributed system, is that the system has to provide that behavior because nothing in any of these systems comes for free. More importantly, if you think about what I said about self points, you might have two different point objects that have the same field values, have the same coordinates. They ought to be the same. If these objects just somehow represent banks, or maybe they're proxies for remote banks, and you know these are actually the same bank with the same sort code, with the same Swift key, the same account number, whatever, then this will give you the wrong answer. Because this will effectively burn through the implementation of these banks and tell you something about it'll tell you something about the way they're implemented. That, okay, you might think of these things as representing the same abstract value, but in fact, we're able to distinguish that at a programming language level. What's this got to do with this idea that an object can know itself? Well, it seems here that the object calling this method is able to know more than just itself, at least when it comes to these two other objects here. What can we do about that? Because this does seem to break this condition. But surely we must have be able to have some kind of object equality comparison, right? So my supervisor, when I gave a rough version of this talk, said, James, your talk is really just one long pun. The pun here is that, well, an object can know itself. So that means writing this should be okay. You should be able to write one of these guaranteed comparisons if you're comparing an object against yourself. If some object reference or something is handed and I don't know what it is, I should at the very least be able to look in a mirror or something and say, is this actually me or not? Because, well, I can know myself, I can recognize myself coming in from somewhere else. In Grace, you could do this by saying, okay, well, maybe we do have this comparison method. In Grace, everything is dispatched, everything's a method. We could do this and we could say, look, it's confidential. And confidential is Grace's term for per instance protected. Why per instance? Because we want an object to know itself and not every other instance of the same class. So we can do something like this. And then what we can do is, given that definition here, which is confidential, well, this definition can be public. It's calling the confidential version. We can actually write a call like this, asking whether two banks are equal. But this call is dispatched. This call, or this method request here, is going to give us many fewer guarantees than the system level one. Because, you know, who knows what B1 is going to do when you send it an equals message. Particularly if you're doing that in a distributed system, in an open system, where you're interacting with code that you don't really know the provenance of. So the question is this actually enough to get real work done? And to finish up this talk, I'm going to argue that it is. So a problem Marx talked about a lot is the grant matcher. And the grant matcher is two people, Alice and Dana, and I guess they're sort of friends, perhaps, I don't know. They had a bet with the program chair how many papers would be shorter than 15 pages, and agreed that if enough of them were, then each of them would donate the same amount of money to the same charity. Okay? But in this permission-free, trust-free, anarcho-capitalist world we live in, they don't really trust each other. But as with blockchain or Ethereum, they're willing to trust some code. So they're willing to trust, for example, this code. They can both see the code, and somehow they can both agree that this code will be run. And so here's an example of a method we think works properly. Alice's donation goes in, and Alice's reference to their charity goes in, Dana's donation goes in. We check to see if the donation amounts are equal. We check to see if these two charity objects are equal. And if they are, we go through and make the transaction. Yeah? Fine. But it relies on double equals. And the question in the object capability community that thinks too much about these kind of things is, can you do it? Can you do it by switching that to an equals operator? And I'm glad Mark is laughing, because I looked at this and thought, yeah, of course it's going to work. Of course this is going to work, right? And if you heard Mark yesterday, code inspection doesn't really work for finding these kind of bugs, especially not when people as devious as Mark Miller are writing the code you have to interact with. Because Mark says, the problem with this, James, is I can do this. Okay, I can make a fake charity object. And the fake charity object has a back pocket with my bank account in it. And the fake charity object always says, oh yes, I'm equal to any other charity you want to do this. I'm equal, give me your money. And then when you give it the money, instead of giving it to an actual charity, it puts it into its back pocket. What can we do about that? What can we do about that? So, again, this is work that obviously I'm doing with various people, including particularly Sophia, who's sitting down the front. But I decided, anyway. What do we do about that? The idea that Sophia and I in particular came up with in relation to a different problem, I'm showing it here because this problem is simpler, said, well, what we do is we do this. Okay. We leverage the fact that we're object-oriented. We leverage the fact, as the paper says, that this equals is left-handed, in the sense that this equals is asking the Alice charity object whether it accepts that the Dana charity object is the same. In the language Sophia and I, or the logic Sophia and I are developing, we might say, we'll assume that if this is trusted, we believe the answer to this. But having done this call, we've only solved half of the problem. Is Alice trustworthy? And the reason the whole works is because perhaps Alice isn't trustworthy and Dana is. And our logic is able to demonstrate that if you just do this call, that fraud is possible. But if you add in this call here, then at least in the situation where one of those charities is trustworthy, this transaction won't go through. Because not only does Alice have to accept that Dana's charity is valid, but also Dana's charity has to accept that Alice is valid. And because each object can know itself, that's enough for this to go through in the cases where both objects are correct, and it will detect something is wrong if one of the objects tries to subvert the system. What happens if both objects try and subvert the system? What happens if both objects are cheating? I promise not to make any references to recent political events in this talk. So where are we? Tower of Babel, Hieronymus Bosch's great picture. If you talk to the Jesuits upstairs, I'm sure they'll be able to tell you lots about this. If you haven't gone up and looked at the Jesuit University upstairs, you should. It's an interesting building. In the beginning, everybody spoke the same language. It was similar. And okay, after a while in America, two countries, two unions separated perhaps by a common language, people started to speak small talk. And the story of the Tower of Babel is that God looked down on what programmers would do and was afraid of what would happen if there was only one programming language. And so he cursed us with the Babel of hundreds and hundreds of different languages, which is more or less where we are today. If you've gone to the postmodern talk, you'll know I don't necessarily think this was a curse. The Catholics have an interesting term which I think is mysterious joy, something like that, which means it's something sad, but it turns out to be good in the end. If we hadn't eaten the Garden of Eden, if we hadn't eaten the apple in the Garden of Eden, we wouldn't know salvation. If God hadn't cursed us when we just had similar and small talk by, making object-oriented programming actually work in the real world and making a lot of people actually want to do stuff with it, we wouldn't have all these languages. Which, let's face it, are the languages in which the majority of programs today, particularly programs, real programs, are written in. And looking around this room, I'm reminded how much this language, this work, and therefore what people do with computers, and when it comes to what people do with computers, what happens in our lives, actually flows down from the work that Christian Nygaard, that Ole Johan Dahl did in Simula. Both language design and how to think about what we do. And then on to Smalltalk, and then there is a direct line right through to C++, to Java, and to a bunch of languages here, many of which are designed by people in this room. But if the language, even if the languages aren't directly designed by people in this room, then features of those languages, understanding of those languages, implementation of those languages, come from people in this room. Traditionally, I would also add Uppsala to the list, but Uppsala seems to have lost its way, seems to have forgotten something, seems to no longer know itself, where it comes from. Okay? And this is something I think that ECOOP is a real contribution. This is why Jan's introduction of Carillon is so great, because it reminds us that what we do is not purely an academic game to game the RAF to get good numbers on Google Scholar. What we do can actually make a difference to people's lives, to society as we know it. The other thing is, I think there's still lots of stuff to do. If you'd asked me when I started designing Grace, is there new stuff about abstraction and encapsulation that you don't understand? I probably would have said, hell no. Simula was 67, it's nearly 50 years old, we understand all of this stuff. But what's interesting is taking some of the ideas, like Williams Cook's strong definition of object orientation, like ideas from object capabilities, and saying, how do we put that into programming languages to maintain security in an open distributed system? Means we're still learning new things about abstraction and about encapsulation. Thinking, okay, we're designing a new programming language, looking at JavaScript and feeling emotionally responsible for it, even though I'm not. But this room is. Is there new stuff we can learn about inheritance? Well, I think there is new stuff. And again, I was surprised. I didn't expect to think there's new stuff we can learn about inheritance. And of course, as I briefly talked, identity and equality. Some of these things are foundational in what the object-oriented model is. And I would argue there is still stuff to learn. There is still stuff to do there. And this is important, and it will be important for designing the next generation of systems and the generation of systems after that. And if you think back to Rust, whenever you find yourself writing a program and making something, whenever you find yourself doing some kind of dynamic dispatch, choosing what you do based on the object that you're passed, whenever you find yourself reaching for the first parameter of a method called self, know yourself. You're object-oriented. Thank you very much.
Okay, so I couldn't help noticing that you're basically accepting this tenet that encapsulation is the same thing as OO, and OO is the same thing as good. And I think that we're very much agreeing on those things, but still you would immediately conclude that reflection is bad, and maybe even that knowing the interface of another object is intruding on that other object. So maybe you should think about the level of protection of an object, the level of encapsulation, and then controlling that carefully instead of thinking of these absolute terms.
So you talked about reflection and knowing the interface of an object. I'll answer those in reverse questions. Si on veut parler à un gendre, on faut comprendre la langue qu'on parle. Yeah, get it? If I want to speak to somebody else, I have to speak that language. Okay? The language, the interface of an object is the language that that object speaks, and if you don't understand it, you can't talk to them.
So you need no encapsulation which is absolute, but encapsulation which has that level of openness.
So, yeah, I mean, the definition says know the representation of an object. So I think you can look at an object and you can see what it looks like, and again, we bring this out in Grace by having tests on types and match statements that work on types, but not on classes. We don't have instance of, for precisely that reason. Reflection, there's actually some I would say, you still want to be encapsulated. And I think there's some very nice work being done, I think, by Stéphane Ducasse and some of the French Smalltalk guys about actually using these ideas of keeping self and using ideas of object ownership and object capabilities, which effectively means, okay, I can only reflect on myself, ultimately, in the same way as we were talking with equals. We don't necessarily have a general reflection primitive that will reflect on everybody. I can reflect on myself. And then if I choose to grant that access to somebody else, I can do that by handing out a mirror. So, yeah, Dave Unger and Gillard's work on mirrors, and then thinking how you do that in object capabilities and reflection.
Thank you for the talk. Even though I know a lot of your work, there was a lot of new and surprising, and I liked it very much. But I was a little bit depressed, and when you reached the Tower of Babel, I empathized with it in the sense that I got the feeling that or rather, in the last 30 years, I have been thinking these issues about pointers, copying, equality, and so on are a little bit arbitrary. You can take any decisions you want, and you can combine them, and they make sense. And you showed us all these issues are still burning, and we have not. I don't think that we have yet found overriding principles that will help us design them better in a way that work together, except of know thyself.
Thank you.
Is that so?
Sure. So Fear always asks difficult questions, and often the best answer is just sure.
It's also a short and sweet answer. Any more questions? Otherwise, we'll thank you again.
And thank you once again.